This is Wireless Transfer of Power, an Electrical Engineering Science 2 presentation by Charles Lockridge. Wireless power transfer is a promising technology. Recently, we have seen more practical applications of the technology in things like wireless phone chargers, toothbrushes, mouses, headphones, biomedical implants, and etc. But the concepts are nothing new. The basis for wireless power transfer is electromagnetic induction, discovered by Michael Faraday in the 1830s. He found that if he passed a magnet through a loop of wire, a current was generated. Conversely, electrical currents produce magnetic fields, so it is not hard to imagine how this could be applied to conduct wireless power transfer. In the 1890s, Nikola Tesla became the first person to fabricate a wireless power transfer device, the Tesla coil, based on the principle of electromagnetic induction that Faraday had discovered. And here is a basic schematic for a wireless power transfer device using electromagnetic induction. Like I said, it is very simple to perform this kind of wireless power transfer. A current is passed through a transmitter coil, which generates a magnetic field, and somewhere nearby is a secondary coil. The magnetic field generated by the first coil also passes through the second coil, so now, because of electromagnetic induction, there is current flowing through the secondary coil as well. It is just a matter of circuitry to then use that current to power something like a toothbrush. So the method I just described on the previous slide is known as inductive coupling. Other methods of wireless power transfer exist, such as capacitive coupling, which uses electric fields to transfer power. Compared to inductive coupling, however, capacitive coupling is thought to be less practical and more dangerous. Because it uses electric fields, it can be interfered with if there are certain materials, such as conductors, in the dielectric space. The electric fields are also potentially dangerous. However, a drawback shared by both kinds of couplings is that they are relatively short range, and they become inefficient at higher power levels. To conduct wireless power transfer at significantly greater power levels and distances, microwaves and lasers are used instead. Already there's fairly similar technology in how radios transmit and receive signals, but the difference is in the priority. Radios depend on the quality of the signal to convert the waves into information. Meanwhile, if the goal is power transfer, as it is here, it is necessary to focus on the quantity of the signal being transmitted, not the quality. In that regard, microwaves have incredible potential for efficiency and distance, but as always, there are challenges to overcome. Microwaves, because they are waves, they propagate, resulting in power loss, and there's also radiation to consider, which may damage nearby life or even technology. The interference of other invisible waves must also be considered. Alternatively, lasers may be used to transmit power over long distances. As long as there's line of sight, a collimated laser beam, which would be a laser with parallel rays, can beam power to a device, but there must be line of sight. Like the other methods, laser power transmission has its drawbacks, but the cons of all these methods can be mitigated, making them more than just promising technology. Hopefully the future holds something like the wireless world that Nikola Tesla envisioned.